In this video, I want to take a look at some more complicated examples of the U substitution. Just some things to watch out for that you might, subtleties in it. Okay? One of the things I also want to point out is that U substitutions, it's not always clear what to do at first. Sometimes it is, sometimes it's clearly something inside, and that's what you let U. Sometimes it's a little less obvious. But I really want to emphasize that you can do whatever you want. However, in fact, I think of this in terms of, mathematics. People think of mathematics as a rigid set of rules that they can only do certain things. No, you should think of it as a system that sets you free, that you're free to do anything you want. But of course, with freedom comes responsibility. So you can do whatever you want, but do it right. So, for instance, I can let U be anything. Well, the thing I see here is the stuff in parentheses there is x cubed. So I'm going to let U equal x cubed. So then du, of course, would have to be 3x squared dx. And I'm thinking, that's pretty good. I've got an x squared dx in here. So if I throw an extra 3 in and take a 1/3 out, so the 3x squared dx there just becomes the du. I'm looking at a 1/3, the integral of sine squared u times the cosine of u du, right? This turned into a u, that turned into a u, and the 3x squared dx became the du. So there, I've done a u substitution. Now I'm looking at this thing saying, can I integrate that? Now, one of the things here is this is sort of a subtle set of parentheses that we don't always see, that sine squared u literally means, I'm going to write the 1/3 out in front here, literally means take the sine of u and square that. So this sine squared, there is a set of parentheses where the inside function is the sine of u, and the outside function is the square of that. Right? If you take a value of u, you'd find the sine first, and then you'd square it. So the inside function here is the sine of u. So I'm looking like I need to do another u substitution. So if you do a u substitution and another u substitution, that would be a double u substitution? So let's let w equal the stuff in parentheses here, sine u. So dw would be, take the derivative, cosine u du, and there's my cosine u du, which is going to turn into, that's supposed to be a dw here, right? dw is cosine u du. So I've got 1/3, the integral, sine u now is just w, so this is w squared times dw. Right? Every time when you do one of these substitutions, the integral should get simpler because something big is all being swallowed up into a du or a dw in this case, right? The chain rule pops that out, and this u substitution pulls it back in again. Okay. So anyway, now I'm here, just the integral w squared. Well, I can handle that. I've got a 1/3 out in front. I'm going to have a w cubed over 3 plus a constant. W then is sine u, so this is 1/9 times the sine of u cubed plus c. And then what was u? Where are you? There you are. U is x cubed, so coming back down here, I've got 1/9 times the sine cubed of x cubed plus c. Okay. Now, it's possible that you could have done this differently. The thing is, you don't always see the best u substitution to do, but you do a u substitution and then see where it gets you. That is, I made the choice of, where am I here? Sorry, this video started right here. I made the choice of u equals x cubed. Because of that, du was determined to be this, and this is the integral I got. Then I had to deal with that. It's possible that having done this u substitution, I actually see that this one, that one, I can put them together. So if I put this u in here, that maybe I could have just gone straight into w equals sine of x cubed. So let me do this all again here. So I've got an integral of x squared sine squared x cubed times the cosine of x cubed dx. Okay, this is the one. This time I'm going to do just a single substitution. And another thing I want to point out in this is that you don't always have to use u. I mean, obviously I used u and w here, but you can use anything you want. And for the sake of in memory of one of the guys I went to grad school with, he always did capital A substitutions instead of u substitutions. So I'm going to let A equal the combination of both of those substitutions. That is, I had the sine of u, but u was x cubed. So I had the sine of u here, but u was x cubed. So I'm going to do the sine of x cubed. What's dA? Well, the derivative of this thing. Well, this would be the cosine of x cubed times 3x squared dx. All right, there's a chain rule in taking that derivative. I see I got a cosine x squared dx. There's my cosine of x cubed x squared dx. I'm just missing the 3. So throw a 3 in, take the 1/3 out here. And so this becomes an integral, 1/3 out in front. The sine squared of x cubed. Remember, there's hidden parentheses in there. That literally is the sine of x cubed squared. So that's actually an a squared. And then all the rest of this stuff, 3x squared cosine x cubed dx, 3x squared cosine x cubed dx, that's the dA. So in one u substitution, or a substitution in this case, you get right to this point, and now you're going to integrate it to be 1/3 times a cubed over 3 plus a constant, and then the a can be substituted back in, and you're looking at 1/9 sine cubed of x cubed plus c. Okay. There was nothing wrong with doing it the other way, doing the two substitutions. There's also nothing wrong with doing it this way. You may not see the best u substitution to start with. That's fine. Make a substitution. Figure out the du. Plug it in. See what you get. If what you get needs to be substituted again, then substitute again. Right? One of the things I found as I was first learning these things was that if I found myself doing two substitutions in a row, I would look at what the composition of it is. So put the u inside here. Look at the sine of x cubed and say, could I have recognized ahead of time that bigger substitution? And with, sometimes I look at it and say, no way, there's no way I would have recognized that. And other times it's like, well, yeah, maybe I could have, because I could see that there's a double chain rule in this one. Well, if you can see it, great. If you can't, do the smaller substitution, and then follow it up with the second substitution, right? If you get to the point where you can see these bigger substitutions, then by all means do them. Okay? Now, how much time? I want to do a couple others that are a little less obvious. How about just something like this? The integral of the natural log of x over x. I point out this one just because the natural log doesn't look like its derivative. Sines and cosines, they kind of look like their derivative. Polynomials, they look like their derivative. Log x and 1 over x, they don't look the same. But you got to get used to recognizing them together. In particular here with the log x and the 1 over x, if I let u equal natural log x, then du is 1 over x dx. And it's like, wow, I've got all that stuff. The 1 over x dx is here, and the natural log of u is in the numerator. So this looks to me like this is just u times du, right? Rewrite this as the integral of natural log of x times 1 over x dx. That's this and this are the same, right? Just written differently. And so this is now just u du. Okay. So that integrates to u squared over 2 plus a constant. Plugging back in, this would be the natural log of x squared over 2 plus a constant. Okay. Thinking now with natural logs, there's another set of integrals that look a little different. You got to get used to these kind of things. If I had something like this, x to the 4th plus 3 under x cubed dx, okay, So there's a completely different problem from the last one. When there's parentheses in there, it's quite often pretty clear to say, oh, let u be the stuff inside parentheses. When there's not, this is where it gets a little less clear. But here's some things you got to be looking for, particularly with things like that. If the degree of the polynomial in the denominator here is 1 bigger than the numerator, then there's a possibility that this might work, and it does in this case, because this is the example I'm giving. But let's not use u or a. Let's do something else. Here's one of my favorites. Let's let smiley face equal x to the fourth plus 3. Right? Then d smiley face is 4x cubed dx. I got the x cubed dx, so throw a 4 in there to go with it, and the 1/4, take it out. Just multiplied by 1, right? So I've got 1/4. The 4x cubed dx, this stuff in the numerator here and there, that's the d smiley face on the end. This denominator is smiley face. I said smiley face and wrote a theta, so smiley face. That's in the denominator, so I've got a smiley face in the denominator and just a 1 left in the numerator, because all of that stuff got used up, so that's all times 1. So this is now 1 over smiley face d smiley face, which would be the natural log of the absolute value of smiley face plus c. Okay, and smiley face then was the 4x cubed plus 3. So this equals 1/4 the natural log of x to the fourth plus 3 plus a c. You might notice that I lost the absolute value signs. I wrote them as parentheses. That's because I just know that x to the fourth plus 3 is always positive, right? X being positive or negative, raise it to the fourth power, that's positive. You add 3, it's still positive. The smallest this could be when x is 0, this could be 0 plus 3. So I don't need the absolute values just because smiley face is always positive. Okay. So anyway, there's that one. I am going to do a couple more in the next video. I'm just running out of time here. So, all right, next video.